Okay, guys, how many total pi electrons in this compound?
I say 12. I say 26. So one of us is incredibly low. Oh no, I just got somehow
Anybody?
10 extra pilots.
14 pairs. 28.
28.
It's like 28.
Oh, I see what it is. On the bench.
28 total? 28 total? Yes, that's the answer. How we doing? Yeah? Okay, guys. Physical properties. Let's see. Alkanes handout. We'll get there. Before we get there, though, any questions about acid-base chemistry? Acid-base chemistry, I think we did not do the last two in class, is that correct? We did those two, we did not do this one? Is that correct? How do we do on this one here? Any questions about these two?
So the left one is stronger because of the resonance, right?
The last one or the
The left one. That is.
What's the base here?
Oxygen on that one and nitrogen on that one. No basic atom. The base.
What's the base here?
Nitrogen.
What's the base here? This guy here? Okay.
Oh, I see. It's not comparing.
And this is the acid? Okay.
It's too late.
Okay, how do we do so far? Which side is favored? Acid over here has a pK of 10. The acid over here has a pK of what? 5. So that's referring to the pKa of the conjugate acid. Which side's favored? Left or right?
Left.
Correct. Left side is favored. Favored side. This is called pyridine. Is pyridine strong enough base to fully deprotonate this compound, which is called what? What functional group is this? What precise functional group is this?
Phenol.
Phenol or phenol. It's a phenol, but that is actually phenol itself. I mean, you can have substitutol around and still be a phenol, but that is phenol. Is pyridine strong enough to fully deprotonate phenol and to fully go over this way? No, it's not. It does not go this way. Majority sits over here with pyridine has done nothing. This side's favored. Pretty straightforward. How are we doing? You need a much stronger base to fully deprotonate phenol than pyridine. How about down here? This was NH2, yeah? What's the base down here? It's only one molecule. Well, that could have been in all just one molecule. It doesn't matter if they're two different molecules. What's the base down here? Yeah, it's the amine. By the way, did we clarify what are good bases? Anions, typically, or what?
sp3 nitrogen.
The only thing that's neutral that's a good base is sp3 nitrogen or sp2 nitrogen, decent base. And nitrogen up there was sp2. It's not a very strong base, but it's okay. Any other thing that's neutral is not going to be a good base. That's not a good base. It's all neutral, and there's no nitrogen there. That's the starting point for looking at it. I mean, there's nothing that's an anion, but this is a neutral nitrogen. There's your base. Where's your acid? Well, I mean, there's a neon sign here. That's a carboxylic acid. The H is acidic. That's why it's called an acid. You got a base and an acid. So what's going to be the result when the base, what does the base do?
Except
It takes the H. Someone say donate?
Yeah.
Don't donate anything. It takes an H. So take that H. Now, internal mechanism is a little bit, we could maybe show an intramolecular mechanism where this takes this H. It may be intramolecular or it may be intermolecular. We can show a totally different molecule and this takes the H of a totally different molecule. In the end, I'm just going to show the product. And what's the NH2 going to become? NH3, right? The lone pair bonds to an H. Boom, boom. And what's over here?
Now it's what is it, ester?
That's your anion, right? And we've got charge here. I mean, if you want to do it intermolecularly, you can draw the H bond there. These electrons take the H. Where do these two electrons go? They move on to the oxygen and become the third lone pair. That's why there's 3 lone pairs there. Nitrogen now made another bond to H. And lo and behold, it's a positive charge. I mean, it's all there. Which side's favored? What's the acid over here? 5. What's the acid over here? This guy, what's his pKa? 10. Which side's favored?
Right side.
This side's favored. Weaker acid. Think about it. This molecule predominantly exists like that. Just minding its own business. That's how it predominantly exists. This is an alpha amino acid, building block of proteins. At neutral conditions or without anything going on, this is how they exist. 2 charges. Net neutral, but it's 2 individual charges. What do you call something that has 2 charges? Starts with a Z. You ever heard the term?
Zwitterion.
Who's that heard? What's your name?
Michael.
Good job. Very nice. Nice and loud there. Took your vitamins this morning. Good. Zwitterion. Yeah, that's how alpha amino acids exist. But we know that from assessing the chemistry and the pKa's, right? I mean, this is what we predict. But how would a pH influence that? That was the next page, right? Back over in the physical properties, there was the acid-base extraction. I briefly mentioned it, but make sure you go back and look at this. Separating compounds using a separatory funnel and also taking advantage of acid-base properties. Separatory funnel in your drawer, most expensive piece of glassware in your drawer, like this. Very nice. Neat Teflon type stopper. For separating 2 different layers. Try to pour it out the top, they ain't going to separate, but you drain them out the bottom, you can separate the 2 layers. In this scenario, we have an organic solvent. Basically, look at the compounds here. This guy's acidic, it's a carboxylic acid. This guy's not. This guy has a pK about 5, that's about 16. Okay? We can deprotonate this guy with sodium hydroxide. That will become an anion. And if we're using water, like aqueous sodium hydroxide, the anion will prefer the water. This compound here will not be deprotonated. It will remain neutral. It'll prefer the organic solvent. But these two will separate. As the layers separate, your compounds separate. Then you can drain one layer into one flask and one layer into another, and you have separated the compounds. To get the neutral compound back, you can just distill off the organic solvent, evaporate it off, and you'll be left with the organic compound in the flask. Here, if you distill off the water, you're going to have the sodium salt. It's also hard to distill off water. You can treat this with acid and put the proton back on. Right? I mean, this is an anion. You treat this, what's your favorite strong acid? ACL? That works. Okay. What's the acid here? ACL. What's the base? That anion. Is an anion a good base? Yeah. Anions and nitrogens. This is going to take the H. When it takes the H, you end up with, right, that plus what? Conjugate base, Cl minus. Is this equilibrium favored? Well, this is strong acid. Its pKa is like -5 or -7 or something. This is a carboxylic acid, pKa of about 5. Which is favored, -5 or +5? +5. By how much? 10 to the 10. That's like a gazillion. Yeah, it's highly favored. You treat it with ACL, you're going to convert it to this. Now, if this is not soluble in water, it may precipitate. Or you would have to somehow isolate it some other way. So there's a couple of things we had to go back and touch on. Any questions while I'm getting it together here? Got to make room for these lab reports. Y'all should be dying to turn those lab reports in. You've had them for a while. Thursday lab, if you'd please submit them to the center. Any Thursday lab? Nope. Thursday lab? Nope. Okay, Friday lab.
Oh, right. That's a
My section is definitely C.
Friday lab.
This is Friday. Those are
Already picked up there.
You sleep blue black. Oh, right. Yeah.
Which lab is
There's
Which one's it?
Delirious for the cell bio testing.
Okay, the alkanes, Cyclo Alkanes handout. We do have a an outline to go with that. Lab this week is a continuation of last week. You'll have roughly about 1 hour to finish everything up. Should be enough. Then we'll move downstairs for lecture, and it will include lecture material.
If we were able to finish up everything on Friday, do we need to show up to lab or just meet in the class?
No, you just need to figure out when we're going to be downstairs.
Yeah.
I don't think you need to show up. You need to just. Importantly, before you come to lab, you need to make sure that you have assessed your data. See if there's any red flags or anything. Because after this week, that's it. What you don't want to do is just kind of blow by this week and you got everything, and then you sit down this weekend, you write your report, and you're like, uh-oh, my melting point is way wrong. Well, you should have did that before you come to lab, so that's your chance. Okay. Uh-oh, my IR is low quality. Well, look at it before Thursday or Friday, and if it's low quality, then run it again on Thursday or Friday. Any other questions about lab this week?
Are we gonna just meet in lab tomorrow?
Do what?
Like, are we just meeting in lab?
Yes, let's meet upstairs, I think, this week, upstairs. Then we'll go down after about an hour. Then next week, I think we're doing recrystallization. There is a video about that on the YouTube page. Okay, conformations, alkanes. We left off, we did nomenclature. Any last questions about nomenclature? The molecule on the workbook. Sometimes try to give some questions there. This molecule, cover of the workbook, yeah. It's got some rings here, and it's got what's called a side chain. This side chain coming off that ring. What common name is that coming off there? That's a common name for that substituent. How about this? What is this sort of chain coming off of this carbon? What is that? In the end, when you see molecules, you can ask questions about them. Yeah? Wonder how many total pi electrons are in that compound. Wonder what's the most basic atom in that compound. What's the hybridization of the oxygens in that compound? And guess what? If you want the answers, show them to me and I'll quickly give you the answer. Stop by. Always look to test your knowledge in molecules you see. Okay, the next page I think we'll do in lab. Some stuff there, including condensed. Take a look at this, maybe real quickly. I'll let you do these two on your own, but you need to get used to condensed formulas. It's not strictly just a pure formula like C20H14NO3. That's just pure formula. This is somewhere between pure formula and structure. Now it's closer to just formula, but there's some information here. Sometimes this is called a linear formula, linear structure, because it can just be typed linear. But it does give you enough to know structure. For example, this here can be turned into that line bond structure. Because we have two methyl groups where? On this carbon. And then what's on that carbon? Well, it looks like an H. Then is the H bonded to both carbons? No. It's only bonded to one, because hydrogen only makes one bond. So this carbon's actually bonded. So really we got a carbon with two methyls. So methyl's a CH3, right? Sometimes I often just do carbon with two methyls and an H, and then it's bonded to a CH2, and then that's bonded to what? An OH? I mean, that and that above is the same thing, just pure line bond structure. You need to be able to recognize and put structures together from these so-called linear formulas for linear structures. Here's two to practice on, and we'll do these a little bit later, perhaps in lab. And we'll look at the rest of this page a little bit later as well. Cyclo Alkanes. We'll look at this a little bit later, I believe. In particular, we'll focus in on cyclohexanes and the conformations of them. Typically covered at the intro level here. There's other cyclo alkanes. We'll look at the piece of formation, what that means, etc. Isomers below. There's some examples. But let's get to conformations, because this is sort of the meat and potatoes here. I want to make sure we have enough time. We'll fill in the blanks for that other stuff a little bit later. We got the blue, that's kind of our outline. And then this is sort of our reference pages, handouts here. Conformations. And we'll do a conformation of ethane. Okay. Ethane. Looks a little funny just to draw it like that, because that's just a line, right? CH3, CH3. That's what we got here. Two carbons, and each carbon has three methyls. Okay? Sigma bond between two carbons, right? What do we know about the sigma bond? It can rotate. Since it can rotate, now I'm rotating the bond, what does that do to the H's? Rotates them, right? Now usually I'll just do this. Now, since it can rotate, what we need to be able to ask or assess is, what's going to be the preferred conformation? A conformation is, what's the definition? Well, the definition is at the top of the blue page. You can read it. Conformation is basically the relative positioning of groups to each other. And if it can freely rotate, you have a huge infinity number of conformations. As this rotates, that's a conformation, that's a conformation. They're all conformations. Well, what's the most preferred? For example, if this H is here, is this H going to be preferred to be like that? Or maybe like that? Or what? Another thing is, well, how do we draw these on the board? Okay? We draw these by drawing Newman projections, and that's the second paragraph there, and we'll do that. Newman projection I also call circle, circle, dot, dot. Remember that? Okay. I don't know if I'm too old or what, but still have that in elementary school? No. No? No circle, circle, dot, dot? Okay. Newman projections of alkanes. Now, in this handout here, this is showing the idea of looking at the relative energies of different conformations of ethane. And this is as we rotate, degrees of rotation, and this is some type of arbitrary energy. No actual numbers here. The main thing is relative. This is higher in energy than this. This is a conformation, and this is a Newman projection. What is that projecting? How do we draw these? Well, let's do that on the board. We flip over. There's different ways to look at molecules. Here's that thing. But it's not showing the bonds, right? We can show the bonds out like this, showing the tetrahedral nature of each carbon. But this still has limitations. But we can look at it like that. Carbon. 1H straight up in the plane. The other carbon over here, this H straight down. So that's like that. Look at this carbon. 1H forward. There's the H forward. And 1H back. There's the H back. And so that's a standard tetrahedral carbon, right? Over here, 1H straight up, 1H forward, 1H back. This is not a good view, though, to do rotations with. A better way to do rotations is the Newman projection. And that comes from looking at this molecule not from where you're looking at there, but looking at it through here. So I'm going to turn and let you look at it through here with me. Okay? Looking at it through here. So what do you see now, and can you draw that on the board? Now we got one carbon directly in front of another. You do this like this. Start with a circle. Okay, sometimes it will be a circle, sometimes it will be oblong, egg-shaped, whatever. And then you put a dot in the middle. Circle, circle, dot, dot. Okay. The dot in the middle is actually the front carbon. Okay, we're trying to draw this on the board. I actually draw it just like that. That conformation. Not that conformation or that one, but that one right there. Front carbon, we have an H going straight up. Now, I say straight up, it's actually leaning towards you guys. But for this purpose, it's either going to be straight up, sort of in the plane. So there's a little bit of sort of, we have to assume that, yes, these are coming forward. But it's going straight up, so I draw an H straight up. I've got an H going that way, sort of towards 4 o'clock. H towards 4 o'clock. I've got an H coming this way, sort of towards what? 8 o'clock. There's the front carbon. Now the back carbon, what do we see? First off, if you're looking straight through here, the back carbon is sort of hidden. Okay? But it's back there. And if this was kind of a big disk, you wouldn't actually be able to see the carbon, but you can see the H coming down from it. The carbon is back there. You can't really see it, but you can see the H coming down from it. We draw the bonds from the back carbon off of the bigger circle, as if you can't see the remaining bonding to that carbon back there. It's hidden by the front. Okay? You've got an H coming that way, sort of what, to about 2 o'clock, off the back carbon, and then you actually have an H here. There's the molecule drawn as a so-called Newman projection. It's a different view. This is much easier and useful for doing rotations or conformations. Newman was a chemist at Ohio State back in like the 60s and 70s, and he developed this drawing method. I knew someone who worked with Newman. Don't tell him I told this, but he used to wash his coffee cup out with the same brush he used to wash his flask out with. You know, the old chemist. That's what I was told, but that's a good story. All right. So that's what's shown on the over here. So these are Newman projections. Now this is actually shown Eclipse. This is sort of like what we have. Let's go through this. We've got some terminology we need to look at. Forget about that. We'll do it here, then we'll go back and look there. If I start here and I rotate the front, there's actually 2 different conformations that we can name. We can start with that conformation. This is one in which the front H is directly in front of the back H. It's like it's hiding it. And what do we call it when like the moon is hiding the sun?
Eclipse.
Eclipsed. called an eclipse conformation. Okay? Now, if we rotate the front a little bit, by the way, how much are we rotating when we go from here to there? By the way, how much are we rotating if we go from here to here? 360? Okay, good. What if we went from here to there?
180.
180, good. What if we went from here to there? 90. 90. So that's half of 180. All right. What if we went from here to there? How much is that rotating? Well, let's do it again. To there. And again. It took 3 to get to 180. So it must be,
60.
each one must be 60. That's called math. Okay? That is, look at this one. There's 180, right? So if we do it boom, 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 each one was 60. Yes. Let's rotate it 60 degrees, which is a common rotation amount. That has a different name. It's no longer eclipsed. There's no longer an H eclipsing the back one. That's called staggered. Staggered. What'd someone say? What did you say?
Staggered.
Okay, I didn't hear you. That's called staggered. Now, we rotated 60. Let's rotate another 60. What are we back to? Eclipsed. Let's rotate another 60. Staggered. Eclipsed. Staggered. Eclipsed. This is going through the same rotations. It's starting with, this is actually eclipsed. Okay? When you do a Newman with eclipsed, yes, the front H is right in front of the back H, but when you draw it, okay, if we have one H straight up, I'll do it real quick. You're like, the other H is right behind this one, so how do you draw it? Well, you do typically sort of draw it a little bit to the side, so you can kind of see it a little bit. Otherwise, you wouldn't even know it, that you even drew it. So when you see it like this does imply that the dihedral angle is 0 degrees. What is a dihedral angle? Di means 2. Hedral refers to planes. Okay? My fingers. What is this angle of my fingers? 90 degrees. Okay, ninth grade geometry, right? Okay. Now, I'm going to blow your mind. All right? That's one plane right through here. What if I make it 2 planes? I got this plane, 90 degrees. What's the angle now?
180.
It's still 90. This is called a dihedral angle because you're dealing with 2 planes, but it's still 90 degrees. Right? It's just separated into 2 planes. Okay? That's called a dihedral angle. That is, the H is in the back, and this one's here. What's that angle? Well, if it was here, that was 90. What is this?
0.
0. 0 is fully eclipsed. This implies 0 degree dihedral angle. But it's just drawn a little bit to the side so you can have it there. Okay. So, this is a fully eclipsed. Eclipsed is not good because you got the H's. These are electrons in these bonds. They're close together when they're eclipsed. And that's not good. Eclipse is never good. Staggered is always better. If you rotate this a little bit, you get to stagger. The electrons are further apart. With the electrons further apart, the system is more at ease and lower energy. So as we rotate, we'll start here. By the way, are they rotating the front or back carbon in these projections?
Back.
Yeah, they're rotating the back. So I'll do that too. They rotate the back. There's the beginning. It's certain level energy. As you rotate, the energy is going down because we're... But typically you go in 60-degree intervals. And you get to this one. And the energy came down to its lowest point, fully staggered. Then as you keep going, now you're coming back to eclipsed. And it's starting to rise up, and it's rising up, and now it's totally bad. It's totally eclipsed. Back. And then you keep going. This was the original. Now we rotated at 180, and you keep rotating. We're back to here, and you keep rotating. here, and then there. One rotation. Here's a take home. There's only actually two levels that you rotate through. You have the eclipsed and the staggered. All the eclipses are actually the same energy level. There's no difference between them, because what's the difference between these H's eclipsing and maybe those eclipsing? There's no difference here. There's no difference in the staggers. Below, we'll see a difference. So, understanding what's going on here, how to draw Newmans, understanding the relative energies, terminology, staggered versus eclipse so far. And so this is your diagram label. I'll make sure you know exactly what we're doing, right? We're looking at a potential energy diagram of ethane as a function of, okay? Any questions about that? We'll look at another example below. Below we have butane. To do that, let's do this. Carbon typically is black, so now we have 4 carbons, 1, 2, 3, 4. I'm not going to put the H's on the end carbons. I only have H's on the 2 middle carbons. So that's a CH3, that's a CH3. Let's see what we have here. Now, the Newmans are actually drawn below. Starting here, the methyls are what? Terminology. They're eclipsed. And like I said here, this implies that the dihedral angle is 0 degrees. And so that's that. The methyls in black, they're eclipsed. That's the starting point. Okay? Let's rotate. And by the way, what do you think of this energy with these methyls eclipsed? High or bad or good?
It's high, but it's bad.
High, bad. Yeah. Well, let's rotate. Here they're rotating again. No, here they're rotating the front, right? They're rotating the front. Let's rotate the front 60 degrees to here. Okay? This would be staggered. Okay? We'll come back and name this. This should be lower. And so the energy does come down. Let's rotate another 60 degrees. Boom. Now what do we have here? We're back to eclipsed. But it's not the same as the original eclipse. The original eclipse had the 2 methyls. This has what? A methyl and a hydrogen that are eclipsed. So let's compare the 2 eclipses. Which is worse? 2 methyls eclipsing or methyl and H? 2 methyls is worse because, well, the main reason is, don't forget the H's that are on this. The methyl takes up way more space because it has those additional H's. If I put them on here, we might be able to see that even better. Call those H's. See, that's how the molecule wants to be. Bring it up here, and all this starts to interact. Starting moving it away is better. In the end, methyl to eclipsing is worse than a methyl and an H. That should almost kind of be intuitive. Methyl is larger, right? So, where are we at? Here. So it is eclipsed, but it's not as bad as the original eclipse. So we have C. It went up in energy compared to this, but not as bad as the original. So we're, let's see, boom, boom. So we're there. Let's rotate 60 more here. We've done 360s for a total of 180, so we went from here to here, 180. Staggered. Staggered's always better than eclipse. But look at this stagger compared to our previous stagger, which was that. Is that any better? Yes, because now the 2 methyls are furthest apart, and that is best. 2 methyls furthest apart, that's called what? Anti, or sort of opposite. One's up, one's down. Dihedral angle of 180. Staggered. This previous staggered, what was the relationship between the two methyls? We start with a G. What's it called? Gauche. Gauche, I believe, is German for to the side. So they're sort of to the side of each other. But gauche is not as good as anti. Okay? They're both types of staggereds, but anti is better. So anti is actually better. Anti is the best one up here. It's the lowest in energy. Now if we keep rotating from there, we're actually going to start repeating, because if we come this way, we're back to eclipsed. Let's see. Can we distinguish between our two eclipsed? Maybe we could call that, I don't know if this is a scientific term or not, but what about fully eclipsed versus maybe partially eclipsed? Makes sense, yeah? So we're back to sort of partially eclipsed, H and methyl. That's E. That's just like C, but it's not as bad as A. Come here. What do we got now? Staggered, also called, more specifically, gauche. And that gauche is the same as the previous gauche. So we got F. It is staggered, but it's not as good as anti-staggered. And then we come all the way back for a full rotation, and we're back to A. How many different rotations here? How many different energy levels? Up top we only had 2, because they kept just repeating the same 2. How many total here?
4.
It's actually 4. A, B, C, and D. And I don't like how it, F, what is that up there? Is that an A?
Yeah.
Yeah. I kind of almost wish they had just, instead of E, they had done C again.
Why did they do that? That's weird.
And instead of F, I wish they maybe had done B again. Because these 3 are just like those 3. There's a total of 4 here. Does everybody see how we counted 4? And then you just start repeating. So top there was 2 different conformations as you rotated 360 degrees. Down here there's actually 4. Again, that's just with 60-degree intervals. Because I could just do this. I could say eclipse, and I could say, there's another one. I mean, I could do a million between here and here. We only really defined the 60-degree rotors. Okay. On the previous was just a little bit of, I tried to tell you how the methyls being anti, I mean not anti, but, by the way, did we call these? Yeah, there's another term here. I don't think it was listed on the other page. Methyls are anti. Here we say the methyls are eclipsed, but there's another term we can use. I can maybe say fully eclipsed. A more scientific term would be syn. Syn means sort of like same side. There's syn here, fully eclipsed, and that would be anti. Okay? When there's syn, that's pretty bad, because all these groups get crowded. And this is trying to show you a so-called space-filling model of actually how much space these groups take up. And it's so congested here. That leads to high energy with all these electrons being congested. And up there, maybe you can see that there's less congestion, particularly when the methyl groups are anti. Questions about any of this? Dihedral angles, terminology? We'll do some examples, including drawing Newmans. Let's do one here, see what type of questions come up. Hopefully that up there is a review of what I just tried to tell you. Okay, let's do some examples. Show the following in the lowest energy Newman conformation. Compound here. Looking down the 1,2 bond. 1,2 being as in nomenclature. If you name this, what would be the 1 carbon? 1, 2, right?
Yeah.
Okay, looking down the 1, 2. So looking down, the carbon 1's in the front, then carbon 2. Okay, 1, 2. Newman projection. All right, let me help you do the first one. You want circle, circle? Dot, dot, yeah? What do we see on carbon 1? Remember from the previous page how I stood over here, and there's actually some eyeballs on the previous page looking over here? I can have the molecule and I was looking over here. Let me get right to it. I'm going to stand over here and look through there. Carbon 1 here, carbon 2 there. What do I see on carbon 1?
Chlorine and hydrogen.
It's either going to be towards you, towards behind the board, or in the plane. The F, is it going towards you or behind the board? The F is in the plane. It's drawn on the board. It's coming down to my feet. If I could just take that molecule and hold it over here, the F is coming down to my feet. So I see a carbon with F coming down to my feet, a carbon with F coming down to my feet. This is what I see standing over here. Okay, on carbon 1, I see a chlorine. Maybe I can do the molecule. 1, 2, 3, 4. Let's get rid of these. Make the fluorine blue. It's not on that carbon. Need one more. And the chlorine gray. Chlorine gray going back. Okay, chlorine blue coming here. All right, there it is on the board. All right, I'm looking right here. I can hold it up anywhere. I see a fluorine coming straight down. Let's finish this one up here. Boom. What do I see going to the left, behind the board?
Chlorine.
Chlorine is to my left, going behind the board. What do I see coming towards you guys off of carbon 1? It's not drawn, but it's a
Hydrogen.
hydrogen. Okay, let's look back for carbon 2. What do I see going straight up? This carbon chain. It's actually an ethyl, but it's going straight up, and we can draw it like that. What do I see here going towards you guys? Hydrogen. And it's also another hydrogen. There it is, drawn as a Newman. But is that the lowest energy conformation? Here's a take home. Lowest energy conformations in our example, the two methyls, the two biggest groups were anti. That's a take home. You always want your largest groups anti. That's going to typically always be the best. What's the largest group on carbon 1? Chlorine. What's the largest group on carbon 2? The back carbon? Ethyl. Right now they're gouged to each other. Rotate it so they're anti. And that'll be your answer. Please try to finish that up, get a final answer, and then try the other two. We'll see how you're doing on that when we pick up.